Hey guys, welcome back to my channel. Today we are going to be running lab experiments on my rodents. So right here we have Lucy. She is a female gerbil. And then we have, over here we have Rat. He is a male gerbil, but he acts like a rat, so his name is therefore Rat. Sometimes they like to come out and play. I am going to be extracting their DNA and I'm going to be cloning them. Just kidding. Unfortunately, we are just going to be doing math today. Maybe another time. Today I'm going to be proving that if the vectors u1, u2, and u3 in R3 are linear independent, then these three vectors are also linearly independent. Going with the assumption that u1, u2, and u3 are linearly independent, that could be shown by some amount of u1 plus some amount of u2 plus some amount of u3 all add up to 0. The amounts of them don't matter to us right now. It just shows that some combination of them added together equals 0. Going off of that, since we know that if you add those all up, some amount of each of them, that equals 0, we are going to be doing the same thing but for the w vectors. So we're going to add up some amount of each of them and we're going to make it equal 0. So now that we know where we're going with that, the next step is to sub in what we know the w values to be, because we are comfortable with the u values. We know that they are linear independent. We just don't know for sure that the w ones are. So if we sub in what we know for the w values, we sub in the u values for them, then we can rearrange the equation and hopefully we make it equal 0. Now here what we've done is, now that they've been substituted, the u vectors have been substituted into the w vectors, then I distributed all the coefficients that we don't know, this the a1, the a2, the a3, into it. So we just got like a whole bunch of math right here. And then I collected like terms. So now that we have the coefficients to each of them in front of the u vectors, so it kind of looks very similar to this equation right up here. But instead of using w, it's using v now. For the u vectors, when we have them look like this, when they all equal 0, we're just going to assume that a1, a2, and a3, all of them equal 0. Because the u vectors, obviously, they can change, they can be whatever they want. But these three, on the other hand, they always have to equal 0, and therefore, when they always equal 0, this equation will always equal 0. So we want to find we want to make these, this, and this all equal to 0. So I'm going to use green now because we're getting near the end and green is good. So I just have this part equal to 0, this part equal to 0, and this part equal to 0. And these are a must. It's an obvious that these have to equal 0 because any other number that they equal, you can't guarantee that it'll be linearly independent. So simple math right here. We have a1 is equal to negative a3. Then we can sub that in to here. So we have negative a3 plus 2a2 plus a3 equal 0. Then we have 2a2 equals 0, which means that a2 equals to 0, because 0 divided by 2. And then we have 0 plus a3 equals 0. Therefore, a3 must equal 0. Last one. a1 is equal to negative 0, aka 0. Okay. So this solves the first part of the question. Therefore, when a1 equals to 0, a2 equals to 0, and a3 equals to 0, that means that these vectors are linearly independent. Yeah, so just like before, when I showed that like the a1, a2, a3 all equal to 0, that means that the u vectors are linearly independent. Now I just proved the exact same thing using the w vectors. And so when we have these vectors up here equal to 3 different sets of linearly independent linearly independent vectors, that means that these 3 vectors are also linearly independent. Now going on to part 2 of the question. The next part, we now want to express this equation as a linear combination of the w vectors. So how we do that is we just have a coefficient, we'll use b now, and we're going to figure out what those numbers are going to be so that they can express a linear combination of that. Now what I'm going to do is I'm going to distribute the b coefficient into each of them, and I'm going to rearrange it to make it look a lot nicer to deal with. Okay, I just distributed it and then made the equation look a lot nicer and a lot more like this one. So ignore the blue right now, just look at the red. You see how that equation looks very much like this equation up here. So we can assume that there's a coefficient of 1, 3, and -1 there. That means this equals 1, this equals 3, and this equals -1. I just made all of these equations equal to the coefficients that we discussed earlier, and now it's just simple algebra. So we have b1 is equal to -b3 plus 1. Now we can sub in b1 to this equation, so we have -b3 plus 1 plus 2b2 plus b3 equals 3. Then those cancel out, so we have 1 plus 2b2 equals 3, or 2b2 equals to 2, or b2 equals to 1. We have one thing so far, so now we can sub that in. So we have -1 plus b3 equals -1, or b3 equals to 0. And then last thing to solve, we have b1 is equal to -0 or just 0 plus 1, or b1 is equal to 1. Therefore, if we want to express this as a linear combination of the w vectors, we can do this thing is equal to 1, 1, and 0. And that's the math. Come back for part 2 for the cloned gerbils.